Classes in Statistical Mechanics. Lectures by Professor George Phillies, based on his book, Elementary Lectures in Statistical Mechanics, Springer Verlag, 2000. And today, this lecture is Lecture 22. I'm Professor Phillies, and today, once again, we are going to be lecturing from my book, Elementary Lectures in Statistical Mechanics. However, we are reaching the part of the course which really is a bit less elementary than the rest of it. So today we have reached page 320, aside F, the central limit theorem. And the central limit theorem starts off with an observation made in the early 19th century by the English clergyman Robert Brown. Namely, he looked into water with a good microscope. He was apparently a superb microscopist, and he could see pollen grains. And the pollen grains, instead of sitting there, jittered and moved. And he tried this experiment with various different pollen grains and was able to observe they still moved and observed various properties. And along the way, someone observed, let's not use pollen grains, let's use gas bubbles. And the gas bubbles are in a drop of water in a quartz inclusion, which, since even clergymen of the period knew, the Earth was tens of millions of years old at a minimum, or 100 million years old. There could be no chemical reactions going on at this late date. You had to be observing some innate property of small objects. And there were then huge numbers of observations made of Brownian motion, none of which came to any definite conclusion because they didn't know what to look for. At the same time, seemingly unrelated phenomenon, early 19th century, the German chemist Fick set down Fick's laws of diffusion. And Fick's laws of diffusion said that the diffusion rate of, say, a colored dye through water was proportional to the concentration gradient. And if you were careful to eliminate convection, this is more easily done in small containers of liquid. You can see what's happening. Where did Fick get his laws from? Well, Fick knew about Fourier and the laws of heat diffusion, which was that the heat flow rate was the thermal diffusion coefficient times the temperature gradient. And Fick knew, like any good scientist of the period, that heat was an ethereal chemical element, caloric, which flowed from point A to point B under the influence of a temperature gradient. And therefore he said, well, it's exactly like what we know about heat diffusion, but it's a different chemical element, and therefore the same laws of mathematics due to Fourier must apply. And he ground through everything, and he worked. Thermodynamics was still partly in the future. In fact, what we now know as the second law of thermodynamics, which had to do with steam engines and their efficiency, was already known. The minor detail that the fellow who worked out the second law, this is Carnot in particular, was convinced that heat was a chemical substance and not what we would now think of it as being, had no effect on any of his reasoning, and it took another half century for someone to point out. He may have assumed that phlogiston was a chemical element, but that's actually not used anywhere in the arguments. For example, you never see phlogiston oxide showing up. Okay, so based on this argument, Fick eventually set down equation F1, which was that J, the vector diffusion current, is d grad C. And there's also a continuity equation, dc dt is minus del dot J, which you also see for electrical charge. And based on these, you can calculate how concentration gradients of chemical elements relax. Brownian motion is a purely microscopic phenomenon, or appears to be. Diffusion was or heat diffusion or chemical diffusion was a macroscopic element. You take a metal rod, you stick one end in the fire, you hang on to the other end, and you notice after a bit it gets warm. Yes? Okay, the front part of this, however, is the central limit theorem. And because we are a little late in the course, I am not going to crank through the central limit theorem, but I am going to point out the key parts of my proof of the central limit theorem, which is actually not mine. It is a well-known proof. Okay, suppose we have a variable x, capital X. We're about to get a door slam. And capital X is the average of the sum of a whole bunch of variables. For example, you could take a whole bunch of dice and roll them and ask them what the average die roll is when you roll a specific number of dice n. And you could ask what the distribution is of the sum of die rolls. And the key feature is the little x's are random. That is, they come out of some place that you don't control. The little x's all have the same distribution. For example, you roll a d6 each time, as opposed to rolling 100 d4s and 1 d1000, which curiously will throw off the distribution. And then you have a likelihood for rolling each of the little x's. It doesn't matter what the p of little x is within reason. And you have a sum. The other neck point is the little x's must be independent from each other. So if you roll 100 dice and ask what the distribution of the sum is, the number of pips showing on one die has no effect on the number of pips showing on some other die. If you take the limit of rolling large numbers of dice, the distribution function for p of capital X, the sum divided by the number of dice, approaches a Gaussian. Okay, so what do we do to do this? We introduce something called the characteristic function for little p, the distribution for one die, and we then take p of x, and we then take its Fourier transform, p tilde of k. And we then say we can do an inverse transform and recover the original distribution, the probability of getting each of the original outcomes. The characteristic function has the interesting feature that if you look at p tilde of k and take its derivatives with respect to k, you get out, this is equation f.8, you get out the moments of x. Okay? And all that you are required is that p of x has a well-defined Taylor series and Fourier transform. Okay? And now what we do is to say we're going to simplify things. We're going to replace the variable x with a funny normalized variable in which we have subtracted out the mean, x bar, and we have divided out the width, sigma, of the distribution. And therefore our new variable y, defined in equation f.11, has an average of 0, and it has a mean square width of 1. That's for mathematical convenience. Okay? The overall effort is to determine the form of P of capital Y, the distribution of the sum. And F13 tells us something we're trying to calculate. So far, so good. And F13 says, well, we're going to sum over all of the little y's, what each of the little die rolls show. The probability that each of the little die rolls has that value, that's the product function at the extreme right of F13. And then there's a Dirac delta function, which requires that the sum of all of the little y's, appropriately written, is the big Y, is a particular value of big Y. However, in order to do this, we take the fact that a delta function can be written as integral dk e to the ikx. That's a way you write delta functions, and the virtue of that integral is it's well behaved, it's continuous, etc. And then you start turning the crank. And the core issue in turning the crank is essentially equation f.18. And what f.18 says is that the distribution function p tilde for one of the little dice can be written as 1 minus k squared over 2n plus some remainder, a. The hard part of the argument, which is everything down almost to the bottom of the page, is calculating the size of the remainder a and showing that if you make the number of die rolls big, that remainder a in equation f18 goes away. What do I mean by goes away? I mean it depends on capital N to a negative power, and the negative power is larger than the negative power of n in the other terms, and therefore eventually it becomes small relative to the other terms, and when you get down to the bottom you can write f.24. However, that's actually a hard calculation to do. It requires an integral you may or may not be familiar with, and so we're going to skip the argument from f18 down to f24 and thence to f25. There is one point I will emphasize on the derivation. In the derivation, we start talking about the logarithm, and the logarithm of 1 plus this variable is the variable itself plus some function capital B. There are lots of people who say, well, we'll derive the central limit theorem and we'll just make this easy for ourselves by calculating the logarithm of the central limit theorem, not the central limit theorem itself. Yes? And you should realize there's something funny here. If the argument works for the logarithm of the final answer, it should also work for the final answer equally easily. And if it doesn't, the reason is that when you calculated the logarithm, you simply threw away the terms that are causing all the trouble, and you actually have to deal with these to prove the central limit theorem. It is very difficult in physics texts to find a valid proof of the central limit theorem, which is why I put this in. And if you look hard in your statistical physics text, if you do not see something that looks like equation f.23, you are probably not seeing a legitimate derivation of the central limit theorem. You are seeing smoke and mirrors. And you want to be alerted to this because it is very easy not to realize what a real proof is if you don't see them regularly in your physics courses. Okay. What is the issue here? Why is the central limit theorem interesting? Well, the central limit theorem says that if we add up a whole bunch of numbers that are generated randomly the same way, the distribution of their average is a Gaussian. It turns out there are a lot of measurements you can do in which the final outcome can in fact be treated as the sum of a bunch of independent errors, and therefore the outcome is a Gaussian. Why is this interesting? If the distribution of errors is a Gaussian, then linear least squares fit is the correct way to do the linear least squares fit and minimize the mean square error in the fitting process. If the distribution is not a Gaussian, then linear least squares fit gives you the wrong answer, and there is a large body of statistics concerned with what you're supposed to do instead. The fact that linear least squares corresponds to a Gaussian error distribution was derived by Carl Friedrich Gauss, which is why Gaussians are called Gaussians. Okay. If your distribution of errors is not a Gaussian, or if you do something to warp the distribution, you then have to do, for example, weighted linear least squares fit to get everything to work. or if the distribution is Gaussian but clipped at one end. You have to do what are called robust statistical methods. Well, where might you get a Gaussian distribution that is clipped at one end? Suppose you look at all galaxies of a given brightness and measure their redshift, or all galaxies of a different redshift and measure their brightness. Yes? Well-defined experiment, yes? So we would like to see what the redshift distribution or brightness distribution versus redshift is, because this tells us how far away the galaxies are, and this is a main astronomical problem. Well, you hit the problem that your telescope can't see, especially 40 years ago before Hubble and such not, cannot see galaxies that are dimmer than some brightness, and therefore if you have a Gaussian distribution of brightnesses at some redshift, you have to realize the distribution is clipped. And this means you have to use what the statisticians call robust statistical analysis. That word robust, is a term of art. It has an exact mathematical meaning. And I have seen exchanges of authors and referee reports where the referees did not realize this and said the statistical analysis is highly robust, when it was ignoring the fact the distribution, the Gaussian, was clipped at one end. It was an amusing set of arguments when one side did not understand what was going on. And now we advance to Chapter 24, Lecture 24, the Langevin equation. We go back to the turn of the century and the French physicist Langevin, who actually asked how Brownian motion might work and how you might write F equals ma for it. Langevin was actually known to his French contemporaries for a radically different reason. Namely, Langevin was sued for divorce on grounds of adultery by his wife. And Madame Langevin named as co-respondent Madame Curie, the discoverer of radium, who at this point was a still fairly young and quite attractive widow, since her husband had been run over by a milk cart. Madame Curie is also more known, well, this is before people realized radiation was dangerous, and there were ideas for radium-based medicine, like silver colloid medicine, no physical basis, as a result of which you can readily identify a legitimate Madame Curie research notebook, because it has to be treated as high radioactivity, not low yield radioactive waste. They're so radioactive. If it's not radioactive, it's a fake. Now that we have discussed this little bit of amusing turn of the last century gossip, let us consider Langevin's idea. Langevin said equation 24.1. Well, the left side of equation 24.1 is the ma side of a force equation. It's m dv dt. And then he said there are two forces acting on one of these particles. And one of them is the Stokes law drag force minus Fv, which for a sphere, F is 6 pi eta a. Now this is a fluid drag force. It's not like solid sliding friction where the force is independent of the velocity. There is an important technical issue which was not recognized until much later. Stokes' law refers to a particle moving in a straight line at constant speed. Brownian particles are not moving in straight lines at constant speed. They are doing irregular motion, and the drag force on them, because of the inertia of the fluid, for a Newtonian fluid with no memory, is described by the Bose-Nesk equation. And the drag force on a particle at one time is determined by the velocity of the particles at all earlier times in what is called a memory function. How much does the particle remember its earlier velocities? Well, Langevin ignored this, and it took 70 years for someone to notice the issue and work out there is a problem here but I can solve this, and the answer is it doesn't matter. And then he said, there is another force on the particles. And the other force on the particles is determined by the solvent molecules jostling the particle of interest. Now, if you're listening to someone who has no idea of what a liquid is like, they will talk about the solvent molecules moving in straight lines and bouncing off the Brownian particle and having a collision. This description has nothing whatsoever to do with a liquid. In a liquid, the molecules are fairly close packed. They are always pressing on their neighbor. Their relative positions may move, but on any significant time scale, the solvent molecules do not move in straight lines. That doesn't matter. The solvent molecules still put a random force on the particle of interest. And what Langevin said is, well, we do not know much about this random force, but we do know a few things. First of all, I will claim the random force has no memory. So if I look at the random force at one moment in time and the random force at a second moment in time, the two forces are independent of each other. Furthermore, the random force is stationary. That is, it's an equilibrium system, and the random force at one moment is large and at another moment is small. But if I look at an ensemble of particles at a series of different times, the distribution of the random force is independent of time. It's equilibrium. Furthermore, I am looking at a particle in thermal equilibrium, the Brownian particle. The true velocity of the Brownian particle must satisfy the Maxwell distribution. It must be e to the minus mv squared over 2 kt. Because, gee, that's about chapter 4. Yes, you remember chapter 4, and we proved that the average thermal energy did not change when you went from a gas to a liquid. Well, here we see that returning to us, exactly as you derived. Yes? Okay, so we have the differential equation 24.1, and the solution to that equation has two parts. It has a homogeneous part, which says that the source term, capital F, the random force, is 0. And that's seen in equation 24.2. Right-hand side, the first term, V0 e to the minus gamma t. And that just says that if the particle has an initial velocity, it slows down and exponentially approaches, meaning it never quite reaches a stop. However, equation 24.1 has a source term, capital F. And the force, capital F, transfers an impetus to the moving particle. You see, this is we're in a liquid. This is Aristotelian physics, in which the natural motion of all objects is to slow down and stop. And they stop when they run out of impetus. Impetus is F over m. And so 24.2 has the second term, in which as time goes on, the F of s over m is the random force giving the particles fresh kicks. And e to the minus gamma t minus s is the fresh kicks, each dying out as time goes on. Gamma is drag coefficient over m. The larger the drag coefficient is, the faster the particles slow down. The larger the mass is, the more kinetic energy they have to be sucked out, and the slower they slow down. Okay, that's the velocity. The complication, of course, I said the Boussinesq equation, and in equation 24.3, I have supplied you with the Boussinesq equation force. And the Boussinesq equation force, which is not the random force, does include a Stokes term Fv, but it also includes all this other things. And I'd better emphasize that capital F in 24.3 is not the random force. It's the total hydrodynamic drag on the particle as it moves, and it includes, very last bit of the last term, the t minus s to the minus 1/2, a memory kernel, which says that the random force is determined by the acceleration at all previous times. Okay, so we then make some assumptions about the random force, one of which is 24.4. The random force is has a delta function, correlation function. Random force at one time and at another time are unrelated. And then we come to 24.5, which is the core of what random means. And what is meant by random is that the velocity at one time and the random force at later times are unrelated. If I tell you the velocity at time 0, I have told you nothing about the random force at any later times. The inverse in time statement is false. If I tell you what the velocity is at time 0, I have given you a hint, not much of a hint, about what the random force was at earlier times, because it was the random force at earlier times that created the velocity at time 0. Okay, so we are now going to try to solve these. Now there's an important issue that Langevin did not know. And what Langevin did not know, except his results would have blown up if he'd been wrong, was his statement that the random force has a correlation time of 0, and his statement that the drag force is determined by the velocity at the same time are not independent statements. There is something called the Fluctuation Dissipation Theorem, which shows you that if one is true, the other must be true, and if one is false, the other must be false. So we will now push ahead to equation 24.6 and section 24.2. And what 24.6 says is the velocity at time t at mean square average value has to be 3kt over m. That's just thermal average. That's statistical average. Okay, and this statement must be true. We're at equilibrium, so it's equally true at every time t. And we're going to need that because we're going to invoke the value of v squared at 2 separate times. The statement that 24.6, v squared of t, is just a constant, has a technical name. It's stationarity. We've mentioned this one before. It's the statement that equilibrium quantities are time independent. An important example of an equilibrium quantity is the entropy of an equilibrium system. It is time independent. It does not change as time goes on. If it changed as time goes on, your steam tables, which show entropy of the steam, would have to be date and time stamped so you knew when they were going to be valid, because they'd only be valid at one time. Okay, what do we now do? We now take equation 24.2 for v of t, and we plug it into equation 24.6. And the left side of the equation, which is v of t squared, doesn't change at all and is very easy. And the right side of the equation is now the square of the right side of 24.2, and is this huge thing you see in equation 24.7. And the only thing you have to remember in writing that down is that when you take equation 24.2 and square it, there's an integral from 0 to t ds, yes? Well, when you square it, there are now two integrals from 0 to t ds, and they are independent from each other, so you need an s and an s prime. And the square of these is 24.7. Well, what happens when you square the 24.2 right side? You get of V0 square as the first term, you get two terms that involve V at time 0 times F at time S. And you get one term which is the square of the integral in 24.2. So you have all of these terms. Well, the two terms in V0 Fs are the same, and they have this wonderful property. They involve the velocity at time 0 and the force to the first power at time s. The velocity at time 0 and the random force at a later time are uncorrelated, so you can average the two separately. The random force at time s is equally likely to point that way and that way to the same extent, and therefore averages to 0, and therefore the second term of 24.7 cancels. Yes? The first term, the last term of 24.7 involves the random force at one time and the random force at a second time. And that is solved by equation 24.4, which says that the product of the random forces at two times is 0 unless the two times t and t prime are equal to each other, in which case it's a. So we will plug 24.4 into 24.7 and do the integral, and you end up with equation 24.8. There's an integral in 24.8, but it's just an integral of a decaying exponential, e to the minus 2 gamma of t minus s. Integrals over exponentials from 0 to t are sort of trivial. And therefore you can do the integral, and if you simplify, the equation becomes a equals 6f kt. F is the drag force, kt is the thermal energy, and therefore you can take 24.9, which gives you a, plug it back into 24.4, and we have the mean square random force. And the mean square random force is 0 unless the two times t and t prime, the times at which you measure the random force twice, are equal, in which case the random force is 6f kt. Okay? This is an example of an extremely important general stat mech result. It is called a fluctuation dissipation theorem. The fluctuation dissipation theorem tells you that if you have an equilibrium system and there's dissipation, that is friction, and it stays at equilibrium, there must also be a driving force, a fluctuating force, and the size of the fluctuating force and the size of the friction are tied together. If there was too much friction, the energy of the system would decay to 0. If there was too little friction, the energy of the system would diverge to infinity. Well, neither of those happen. Okay, so that's the fluctuation dissipation theorem. Less obviously, though it's true, the time dependence seen in 24.4 for the random force. Namely, the random force does not remember from one moment to the next how big it is. And the time dependence of the friction force, it only acts on the velocity at the same time, are intertwined. And that's a little less obvious. But that is a fluctuation dissipation theorem, and it shows you what must be true in order to keep thermal equilibrium. Note that the arguments that lead to the fluctuation dissipation theorem are very different from arguments we've used in other parts of the course. In other parts of the course, we might calculate the mean square force on an object due to its neighbors. We could do that. I don't think we ever did it. But that would be a direct calculation from we know the potential energy, and therefore we can use statistical mechanics. Here we said we know there is thermal equilibrium, new statement, and therefore we can calculate what the driving force properties the driving force must have to get us to the right answer. And we hope that if we did a direct calculation and could identify the random part of the force between two objects, we would be seeing what we just calculated. Yes? Two very different possible approaches. The next thing we do is to calculate the mean square displacement of the Brownian particle. And to do that, we write down equation 24.11. And 24.11 defines the displacement of the particle. It's the time integral over the velocity. And we also define a diffusion coefficient, 24.12. The diffusion coefficient is calculated from the mean square displacement. Okay, well, let's calculate the mean square displacement, and we do that by taking 24.11 and squaring it so we get 24.13. Integral from 0 t to ds, integral from 0 to t ds prime. And then we take v of s, and v of s is from equation 24.7. So we insert, or better yet, it's from equation 24.2. And we put 24.2 in, and we multiply it by itself, and we get 24.13. Yes? Well, that looks messy. However, the middle line is determined by the velocity at one time and the random force at later times multiplied together, and that averages to 0. Then we get to 24.14, where I've also replaced the random force correlation function f of y prime in 24.13 with its value. You should note there is something missing from 24.14. Namely, at the end of the second line, there should be an e to the minus gamma s plus s prime minus y prime. There is a term missing, and I'll show you what it is after class. Having said that, we now have an integral which gives us the diffusion coefficient. And with some considerable work, we can do the integral, and I sort of give you some hints on doing it, and you get equation 24.15. And you get that 6 dt is equal to 6 kt over f times t to the first. And then there's a constant term and some terms that die out rather quickly as time goes on. And at long times, d equals kt over f applies. Okay. The relevant calculation is quite tedious. And you have to be very careful to get the upper and lower limits right on integrals, or you get an answer that makes no sense. What else could we do? Well, I just sketch how to do it in 24.4. I say we could calculate the correlation between two successive Langevin equation steps. Is the correlation 0? No, because the random forces at time before the end of the first step gave the object a velocity at time 0, and at later times the object still retains a bit of that velocity. So the successive steps, random steps, are not uncorrelated. Okay. So we've now solved the Langevin equation, and we've found fluctuation dissipation, and we have said that successive steps are uncorrelated. Now let's look at the total motion. The total motion is composed of a sum of random steps. Each random step has a mean square size we can calculate. Successive steps are uncorrelated. Well, there's a correlation that dies as e to the minus f over mt. Successive steps of any length are practically uncorrelated. Yes? Therefore, we have a statistical process which is generated as a sum of small processes. Regardless of the distribution of the first process, the distribution of the large process is Gaussian. And that's the central limit theorem coming in. The central limit theorem, because we have satisfied the conditions for the central limit theorem, gives us equation 24.22. It gives us the distribution of displacements as a Gaussian with width in dt. There is the central limit theorem and the solution of the Langevin equation. Well, now you know that what you're supposed to calculate is the mean square displacement versus time. The outcome is kt over f, where f is the drag coefficient, and you can now test this experimentally. Okay. Well, so that is the Langevin equation, and it's the introduction to everything else that comes later. Interesting homework problems, 24.7, non-successive displacements, you will find is a bit challenging, but it's just you have to be careful with the integrals. 24.1 we've already done. 24.2, what is the pressure of a liquid assuming you treat it with an ideal gas? That's actually quite funny. I've had a student, when I was teaching thermal at Michigan, give me that on an exam. He calculated the pressure of liquid water using the ideal gas law. Try doing 24.4. Present the missing steps to obtain 24.15 from 24.12. Just try doing it and see what happens. We are out of time.